Two particles move with constant speeds u and v along mutually perpendicular straight lines towards the intersection point. At t equal to 0, the particles are located at the distances a and b as shown in the figure. At t equal to 0, this distance is a, this distance is b. What will be the shortest distance between the particles? So let's say at some time t, the situation is as follows. Both particles have moved by some distances. In time t, this particle would have moved distance ut and this particle would have moved distance vt. So let's say this particle is here. So this distance would be a minus ut, and this particle, let's say, is here, and this distance would be b minus vt. So distance between them would be this. We want this distance to be the least. Let's call it L. Let's call it X. Let's call this Y. So L square is X square plus Y square, and this L we want to be the smallest. This will happen at some time, and we need to know that time. So L is the root a minus ut square plus b minus vt square. dl by dt must be 0 for either maximum or minimum. Two can be cancelled. So we have got this equal to 0. So this is the time at which we have either maximum or minimum. We of course want minimum. So let's go for the second derivative test. So dl by dt is this, and we need to differentiate it further. So let's do it here. Square of the denominator, then we copy the denominator, we differentiate numerator, minus, then we copy the numerator, we differentiate denominator, this is multiplied by one more bracket, which I will write here, the derivative of this inside the root only. That's it. Again, 2, 2, 2. Gone. To make it look compact, let me put x in place of a minus ut and y in place of b minus vt. So d2l by dt2 is x square plus y square under root u square plus v square minus minus ux minus vy, then this fellow minus ux minus vy, then this fellow Then this whole thing divided by x square plus y square. This into this root will be gone. Then this power half, power 1, 3 by 2. So denominator is positive. We are doing second derivative test. So second derivative, we want to check if it is positive, negative. Denominator is positive. Let's open the numerator. So we have square of this. So basically we are getting non-negative. So second derivative test points towards minima. So the time that we got earlier, AU plus BV divided by U square plus V square, this is the time that corresponds to the minimum value of L minimum. So at this time, the L that we get is L minimum indeed. So here we have L, and this T we need to put here to find L minimum. So let's create some space here. So L minimum would be A minus U. In place of T we have AU plus BV divided by U square plus V square. Then this whole square, and then B minus V AU BV u square plus v square, then whole square, and then we have under root. So let me write square for the moment. Au square, cancellation. Bv square, cancellation. This can be taken common. This can be taken common. Then we have got v square and we have got u square. So this would simplify to av minus bu square u square plus v square. Now we can take under root. So L minimum is av minus bu mod, then under root u square plus v square. So this is the shortest distance between them at certain instant, and we found out what is t at that particular instant.